Hi, welcome to Weather and Forecasting, and this is Module 1. Before I get started, let me just say that as we're going through lecture materials, because you will have these PowerPoint presentations as PDFs, if it's something that's just simply reading definitions that you'll gain the knowledge by looking through on your own, I will skip right over. I don't need to read to you something that is on a page. And so I'm here to guide you and give you more information than simply what you're seeing on these PowerPoints. I'm not here to read to you what the PowerPoint says. So obviously you are dynamically watching and moving along at your pace while I am also working through this with you. And so if it seems like I skip ahead, I'll typically tell you I'm about to skip ahead, and you can pause, look at those slides, and then rejoin me at any given time, since these are videos and you basically have control over the speed with which you want to learn. So once again, this is our first module, and this is our Chapter 1 lecture, and it's exactly like the textbook shows in its 7th edition. And once again, I am going to move fairly quickly through this information. We're going to begin in Chapter 1 just talking about the atmosphere itself, so specifically composition of atmosphere and what we consider variable materials in the atmosphere, so variable gases and solids, because we'll talk about particulate matter, and things that are non-variable, so things that their percentages or the amount they're present is set in stone. As far as definitions, I'll let you read definition of what is atmosphere meteorology and what is climatology. The scientific method. Hopefully you remember this from your many years of grade school reviewing the scientific method, but science is a fabulous thing in the sense that we can ask a question, develop a concept, which is the hypothesis, determine what we think is going to happen so that we can plan for results, create an experiment, and then analyze what we found. And this allows us to write both positives and negatives. We're not actively trying to prove what we are saying. We are actively just trying to figure out whether what we believe will happen is actually occurring. So, thickness of the atmosphere. The atmosphere is divided up into various layers, and how we divide those layers are dependent on what we want to measure. If I want to measure temperature regimes, I have one sense of atmospheric material that I'm going to measure. If I'm trying to measure it based on particulate matter, that's another form of measurement and naming regime that I'll get into. And then there's one more, which is based on ionically charged particles, also known as our wavelength-based atmosphere layers. And so I'll talk a little bit more about that later in this chapter. But one of the key things to remember about our atmosphere and its thickness is that it's actually a very thin layer when you compare it to the Earth itself. You can think of it as if the apple is the Earth, the skin on the apple really is all the thickness that is our atmosphere. So it's an incredibly thin layer on the exterior surface of our Earth. And what's keeping it on our Earth is simply gravity. Gravity is holding those particles to the Earth itself. So it's pulling it inwards. Composition and vertical structure, we will talk a little bit more about. So I'm going to just wait. I have a few slides that are going to get into this, but the first thing we need to talk about is the gases that make up the atmosphere. And so we're going to put them into two categories. The first category is things that are permanent or stable, things that the percentage or amount of this gas are similar in all places the Earth over, and they are unchanging. So the amount in any given place stays about that percentage. It might be off by just a point something, but it's pretty much within that volume of percentage. And so the biggest one, the thing that makes up most of our Earth's atmosphere, is nitrogen. And N2 is just an inert filler. It's an inactive material in the atmosphere, and it makes up 78% of all of the Earth's atmosphere. The next one is oxygen, O2, and that one makes up about 21% of all the Earth's atmosphere. And once again, these are inert. They are unactive particles. They're not acting with anything. They are simply here filling up the space around us. From there, you can see we have argon, neon, helium, krypton, xenon, and hydrogen as inactive, permanent material in the Earth's atmosphere. The next one is variable gases. Now, these are the ones that are changing. These are the ones that are fluctuating up and down based on percentages as well as changing in place. For example, my carbon dioxide as well as carbon monoxide, so CO1 and CO2, as they go through, are variable based on place as well as variable in the amounts over time and time of year. And so I can go into a city and measure out more carbon dioxide in that location than I would find maybe in a rural area, as well as I can find certain times of year, like in the winter months, higher levels of CO2 in the northern hemisphere, where in the summer months I will find lower levels of CO2 in the northern hemisphere. And so they are variable, they're interchanging, as well as we now have more CO2 in our atmosphere than we've ever had in Earth's history. So these are all examples of variability. The big one on this list, though, is water. And water is the major thing that we will be measuring. Water in our atmosphere is the actor and reactor. It's the thing that moves heat energy all around our globe. So you think of cloud formation, that's just heat transference. I'm taking water and I'm heating it up. That heating it up changes its state of matter from a liquid or a solid, if it's ice or snow, into a gas. That gas allows it to rise, it cools off, it goes back into being a solid or a liquid, and then gravity pulls it back down to Earth. But that transference is energy moving based around the planet. So I take those clouds, put them up in the atmosphere, and I shove them to a new location, and then I drop them down in a new spot. And so this water vapor is the major way that I transport energy from places of energy surplus to places of energy deficit. So in many ways, meteorology in general is a study of physics on a system. I'm just taking the application of everything we know about heat transference and physics and physical understanding of our universe, and I'm applying it specifically to meteorology, to the measurements of my atmosphere and the actions and reactions that are happening within that atmosphere. Water vapor itself, while it says here it makes up 0.25% by volume, at any given place, at any given moment, I can have between 0 and 4% of my atmosphere filled up with water. So I can have quite a bit of water in some locations. For example, if I'm walking through a cloud, that's about 4% of my atmosphere. I am at like 100% saturation. I can't fit any more water, right? If I'm walking through fog, it's just a cloud on the ground, so I am maxed out on my water precipitation amounts, right? And so I can change the amount of water. On a day that's incredibly dry, we talk about low humidity. Obviously, I'm getting closer to 1% or less than 1% of volume of water. On the days when I have high humidity in the atmosphere, I'm getting closer to 4%. But the amount of water in my atmosphere at any given location is sliding on a rubric scale. Ozone is another variable gas, and that actually depends on location. So as I go up into, for example, stratosphere locations and things like that, I might find a depletion of ozone in those locations, where if I go to places like city locations, I might have an excess of ozone. Same thing with methane. It's variable based on place and sometimes human activity. All of these can be variable based on human activity, as well as being variable based on climatology and meteorology reasonalities, so reasons that are produced by those things. Before I get into too much detail about water variation, I'm actually going to flick right over to NOAA and just show you a little bit about CO2 and the Mauna Loa data. And I just want you to see that you can get the data current based on these variable gases, and most specifically CO2, since it's such a huge contributor as to what my climate is going to do. How much excess energy or surplus energy is being stored at any given moment can almost be directly measured based on the amount of CO2 in parts per million. Parts per million, ppms, as you're seeing right here on here, means that if I took 1 million particles of atmosphere and I was to measure out how many of them are any given thing, when I say it's 407, I'm saying that 407 of these particles are carbon. So on that note, I'm going to stop with the video part 1 of this right here, and I'm going to pick back up, back on the slides for part 2.